Exceeding the gold standard of science. Welcome, guys. My name is Brian Osborne. I'm a speaker with Answers in Genesis. I'm here with Dr. Nathaniel Jeanson, also a speaker and researcher scientist with Answers in Genesis. And we're so glad you're here to be here on this particular episode, talking about his book called Traced: Human DNA's Big Surprise, being the subtitle. And we're calling this the new Rosetta Stone to human history. And in this particular episode, we're diving deep into the science and showing how this science we see in this book that confirms the Bible again and again is really, in a real sense, the gold standard that scientists want to see. So Dr. Nathaniel Jeanson is going to flesh this out for us. This is going to be an awesome episode. I can't wait for it. Dr. Jeanson, it is all yours.
Thank you very much, Brian, and welcome to our audience. I'm going to review just a little bit of where we've come from for those who are joining us live. If you're binge watching this, I hope you can bear with us as I go through what we're doing. Part of a longer series. We're now on part 11 by the YouTube counting. You can find our on the Answers in Genesis YouTube page to find the earlier episodes 1 through 10. The big picture focus of this book, as well as this new little mini series within this larger series that we're doing, deals with the male inherited DNA. The physical thing that we're calling the new Rosetta Stone of human history is this DNA-based, generation by generation family tree for global humanity, where you compare the Y chromosomes, the male inherited DNA of men around the globe, and you can reconstruct this family tree. And to see how we can do this, I'll refer you back to previous episodes. And again, here's a screenshot of where you can find more of this. Again, Answers in Genesis YouTube page. You look under playlists, Traced: DNA's Big Surprise episodes. We just concluded a sort of another mini series. If you're watching live, you might recall that we did about 6 episodes. We took a break, then we finished covering the main body of the content in the book, the history of the various peoples around the globe, finishing up with these 4 regions. And what we want to do now in this episode and going forward for this group of 5 is to step back and say, well, how do we know this is true? We've just reviewed all this history. Maybe you're watching this and you're sitting on the fence and saying, you're creationists. It sounds compelling, but I just don't know if I believe it. And maybe you're gung-ho about this, but you want to share this information with other people who are skeptical. That's part of the purpose of this little mini-series. If we went in depth into every little nitty-gritty scientific detail, it would be a super long series and would probably lose most people. What I want to do in this little mini 5-part lesson is give basically a history lesson, where I can give you an overview of here's what's happened prior to it, here's what's led up to the conclusions in Traced, and here's where you can dig into it deeper if you're more technically minded or if you're a scientist by training. But there's a bigger point that I want you to walk away with that I hope this little history lesson will give you. And again, the larger focus is, how do we know that the conclusions in Traced are true? One of the main reasons for skepticism, if you've watched this series or you've read the book and you're still wondering about it, is the fact that it's based on a young Earth framework that is not the mainstream framework. And one of the main reasons then, someone might say, well, I don't know if I believe it, is because it seems to contradict mainstream geology, mainstream paleontology, mainstream archaeology. It doesn't agree with evolution. I'm a biologist by training, so I'm not going to pretend to be an expert in geology, paleontology, archaeology. I'd refer you to the work of my colleagues here at Answers in Genesis and other creation organizations where there's PhD professionals in these disciplines who have researched and published on this. You can go to our website, answersingenesis.org. That's not trying to avoid the question. It's just that's not my area of expertise, so I won't try to pretend to be an expert there. With regards to the question of evolution, I have written a book on this, basically Evolution A to Z. It's called Replacing Darwin: The New Origin of Species, in which I walk through the leading lines of evidence for evolution. And as the title of this book implies, the main conclusion here is not just here's some problems with evolution. It's here's how creation science is exceeding, again, the gold standard of science and replacing Darwinian ideas, replacing the mainstream explanation for the origin of species for that bigger picture question. Not just the narrow human origins question, but the bigger picture. What about animal species, plants, fungi, so forth? That's what this book covers. I won't try to recapitulate that in this lecture or in this little series, and instead I'll just refer you to this. What I do want to focus on, and the history that I would like to cover, is the science as it relates directly or closely, somewhat indirectly, to this question of human origins and human history and in particular to the conclusions in Traced, which is again focused on human history and human origins. And the overarching conclusion, my overarching answer to how do we know this is true, flows from the main criticisms that anti-creationists have given of creation science for decades. And I'm going to give you several quotes. If you've watched some of the earlier videos in this series, you might recall some of these, but these are so critical, and this concept is so critical to answering this question. I want to review it, and I'm going to come back to this concept again and again and again, because we really are at a watershed moment in the creation evolution debate, and Traced plays a key role in this. So going back to 1982, some of the early heyday of the intense public and legal battle over creation science and its role in the public school science classrooms. Here's a quote from Niles Eldredge, famous paleontologist, wrote a book called The Monkey Business. The scientist looks at creationism. Of course, he's not in favor of it, and here's why he says he's against it. Creation science, he says, isn't science at all, nor have creation scientists managed to come up with even a single intellectually compelling, scientifically testable statement about the natural world. Creationists pose no testable hypotheses, make no predictions or observations worthy of the name. And this common thread here then is this idea that creationists need to make testable predictions. They need to make statements that can be tested experimentally in the lab or in the field. And one of the reasons I'm quoting this is because this idea of testable predictions has a long and strong philosophical history. This is what we apply all across the board scientifically. We accept gravity as a scientific idea because it makes testable predictions. What the evolutionists have demanded then is that creation science meet that same standard. They might say, if we broaden our discussion here momentarily to the question of, let's say, animal origins, the origin of animal species, evolutionists might say to creationists, okay, you guys, you creation scientists say that God created different kinds of creatures, that Noah took 2 of every kind on board the ark. Those animal kinds exited the ark, and they formed new species over the last 4,500 years. If that's true, then predict for us, creation scientists, how many new species will form this year? How many new species of rodents will form this year? Predict for us how fast or slow this particular species in the wild will mutate its DNA. Something, that sort of thing is what the evolutionists have been demanding. Something that we can go into the lab and experimentally evaluate. Let me give you a quote then around the same time from a federal court decision that said that a particular Arkansas law, which mandated the teaching of creation science in science classrooms, was not legal. The judge said the reason you can't do that is because there are certain criteria for what constitutes science and what does not. He gave about 5 of them. The one that I'm focusing on here is this 5th one, that science is falsifiable. And he said creation science fails to meet these essential characteristics. He says you can't falsify. In other words, you can't experimentally test and in theory try to disprove creation science, but other scientific ideas you can. Fast forward just to show you that this has been a common pattern. This is just not a 1980s concept. Here's a quote from a popular evolution textbook for university students, usually their 3rd year. Douglas Fatuma and his co-author Mark Kirkpatrick have a whole chapter on dealing with creation science. And they say the most important feature of scientific hypotheses is that they are testable. And of course, they go on to say that creation science, intelligent design, these sorts of things are not science because they're not testable. So back to the question of how do we know that the conclusions in Traced are true when they conflict with mainstream science? And the answer that I'm going to go back to over and over again as I narrate a history of scientific discoveries over the past decade is that I would say we know the conclusions in Traced are true because they are part of a historical progression of discoveries in which successive, testable, young Earth creation predictions keep working. That's a mouthful, but the point is, it's true because it makes testable predictions and it has fulfilled testable predictions. And this is the gold standard of science, both from a pure philosophical perspective and from an apologetic creation evolution debate perspective. This is what has been demanded of creation scientists for decades. And what I'm going to narrate for you over several episodes of this little mini-series is a decade worth of research that's behind the conclusions in Traced. And I want to narrate it historically so that you can see predictions, fulfillments, predictions, fulfillments. There's this underlying pattern that is held true for a significant period of time. So once again, the Y chromosome, male inherited DNA, is the focus of TRACED. How did we get to the point where we could confidently read off human history from this tree? Because that's essentially what this book does, TRACED. And I want to begin answering that question, not by going back to 2013, where one of my first papers on human genetics was published. I didn't start with the Y chromosome back then, but it's part of the narrative. Instead, I want to begin with where the Y chromosome begins to play a significant role. That's more like 2017, 18, 19. So we're going to start there because that's the main focus of the book Traced. And I want to narrate a sequence of predictions, fulfillments for you over several episodes, about 3 or 4 episodes. And then we'll step back and give even more of the backstory of the research in other human DNA compartments that led up to where we are today, so that you can see there's been a long, consistent, coherent narrative. Well, one of the first experimental steps that was taken, that I took, was looking at the rate at which the Y chromosome DNA was changed. So again, we're trying to get a broad overview of the sequence of experiments, predictions, and fulfillments that led up to the historical conclusions for the Y chromosome DNA-based tree. One of the first lines of evidence underscoring these conclusions was looking at the rate at which fathers pass on mistaken versions of the Y chromosome, or perhaps more precisely, yes, fathers pass on the Y chromosome to their sons, but at what rate do they make mistakes in copying it? When the sperm stem cells, if we want to get biologically technical and precise, at what rate do they copy that Y chromosome and copy it in an erroneous way? Well, if you look to the mainstream literature, the answer to that specific, precise question came in parts. I started with the Institute for Creation Research in 2009. I got my PhD from Harvard in 2009, working in basically medical sciences question, and I took a job with ICR to focus on more historically creation evolution related research and questions there. And that also happened to be the time then when one of the first studies was published on the Y chromosome mutation rate. In this case, they did not take a whole bunch of fathers and sons. They took 2 Chinese men who had a known common ancestor in the 1800s. They got the Y chromosome sequences of each of these 2 men, compared them, counted the number of differences, and from that, so they got the number of generations that separated them, they got the number of Y chromosome differences between them, and that resulted then in an experimentally measured rate per generation at which this Y chromosome changes. Now, the conclusions they reached based on that rate was that it fit evolution. The rate at which this Y chromosome clock, so to speak, ticked was rather slow. The Y chromosome rate of mutation was slow enough to imply that the origin of the Y chromosome differences that we see today took hundreds of thousands of years. That wasn't the only study. I was aware of this back then. I didn't quite know what to do with the data. I was working on female inherited DNA at that time, which was highly controversial. There was a whole bunch of papers. I'll talk more about that story in a few episodes. But I left that Y chromosome data alone for a time, thinking, well, maybe just more publications will provide a different perspective. In a sense, that is how it turned out. For the mitochondrial DNA, the female inherited DNA, the conclusion that I landed on was simply that there was a bunch of statistical noise and you had to pool all of the data together. For the Y chromosome data, a different explanation seemed to be relevant. And this is what I mean. I have on this slide here that by 2017, I was aware of 4 published father-son mutation rate studies or men of known genealogical relationship studies, just like the 2009 one, those types of studies. There were about 4 that I was aware of, and I put here there were 2 that are high coverage, 2 that are low coverage. Those are technical terms for there were 2 of high-quality DNA sequences, 2 of low-quality DNA sequences. Let me explain what I mean by that and why coverage is the term that we use for it. And I'm going to show you here that this idea of coverage and quality is not my idea. This is already experimentally established in the literature, and it plays a huge role in interpreting the results that came out by 2017. So I'm pointing you here now to a 2016 paper in Nature Genetics. This was the Y chromosome study from a project called the 1000 Genomes Project. So you can see here in the title, 1,244 men with Y chromosome sequences. That's what they studied. And here's the supplemental information that I'm going to extract an image from. here's this graph, and I'll explain to you here methodically what this is referring to. The Y chromosome 1000 genome study from 2016 was basically a low quality study. It's not one of these 4 that I was referring to, but there's data here that are relevant to these other 4 father-son type mutation rate studies. In 2016, they published, again, what I would call a low coverage, low quality study. Let me back up here for a moment and explain to you very briefly how Y chromosome sequencing works with the current technology that's in vogue. The technology is changing, but this is what they had at the time. This is the technology that was basically being used 2009, 2000 through 2017. And it goes like this. You first get a sample of someone's DNA. You might take just a cheek swab, because that contains cells which contain DNA from, let's say, 1,200 men. Then you chemically extract just the DNA. You separate the DNA in those cells from the rest of the cellular contents. Fine. What you want, though, is the Y chromosome sequence. Then what you do is you bust up that chemically isolated DNA into millions of little pieces. There may be 50 letters long, 150 letters long. They're tiny, whatever it is. You do that because you can, with current technology, obtain the sequence of those tiny snippets en masse in parallel. So you can do it very quickly. So once you do that, now you've got millions of tiny little sections of DNA. Your next task, your next step is to electronically stitch these back together. You have some sort of reference gold standard sequence. You electronically try to align these little snippets onto it. Long story short, the Y chromosome sequence is about approximately 60 million letters long. A whole bunch of it is very difficult to analyze with modern technology. Some of it is repetitive, for an example. So if you've got this tiny little sequence, it could match here, or here, or here, or here, or here, or here. There's a bunch of different places it matches because the sequence itself is repetitive. So where does it belong? Can't resolve that question with that type of technology. Only about 10 million letters of the total 60 million are accessible with this Y chromosome technology that's basically unique sequence. Long story short, there's only a little section that you can analyze. Now, let's just review the process I described. Get your DNA, chemically isolate it, bust it into millions of pieces, sequence the tiny little pieces en masse, and then electronically stitch it back together. Well, how do you know that you've done a good enough job and that you've accurately captured what a particular man's Y chromosome sequence is for that 10 million letter section? This is where coverage comes in. You're going to electronically align those tiny little snippets to this reference sequence, and some will match here, some will match here. In a perfect world, you might sequence 10 million letters of Y chromosomes. That would be a whole bunch of tiny little snippets, and you've captured the entire 10 million target sequence that you're after. We don't live in an ideal world. For reasons not entirely known, sometimes you'll end up sequencing a whole bunch of this little section of the 10 million sequence, and not so much over here, and a lot over here. There's random variation or things going on that we still don't fully understand because it's happening at an invisible level, molecular level, these processes. So the way to compensate for that is just to, in theory, go over your sequence again and again and again and again in hopes that you finally capture all that's there. That's what this idea of coverage represents. How many times have you, in theory, gone over your total sequence? So here's how that number is calculated. Let's say you're interested in 10 million letters of the Y chromosome, and you turn around and you get the sequence of a whole bunch of tiny snippets of DNA that in total represent 10 million letters. That would be called a 1x, one-fold coverage. You've sequenced 10 million letters. In theory, in a perfect world, you've gone over your sequence of interest that's 10 million letters long one time. If you go over, so 10 times 30 would be 300 million. Let's say you go over your little snippets, you sequence of these little snippets, you sequence a total of 300 million letters. That's 30 times 10 million. In theory, then you've gone over your sequence 30 million times. Excuse me, you've gone over your sequence 30 times. 300 million versus 10 million, 30-fold coverage. So the point is, that's what this idea of coverage represents. It's what's the chance that you've actually accurately captured what you're interested in. Even if you didn't follow the technical details, that's what's behind it. The 1000 Genomes Project for the Y chromosome had an average of about, I think, 4-fold. It wasn't very good. And so the researchers were interested in answering the question, well, how much did we miss? In theory, we haven't gone over that sequence very well. So of the 1,244 men, let me make sure I got the numbers right, about 143, I think, they separated it out, and then they went over that sequence a whole lot more times so that you have high coverage, high quality. And then they compared, of those 143, let's see what the high coverage versus the low coverage looked like. That's the whole backstory to this graph. This graph represents, here's all the DNA variants that we missed because we did low quality. Again, this is not a father-son mutation rate. This is background to what I'm about to tell you and why it's so relevant and why I think the conclusions in TRACED are valid. This big, tall bar right here, 3,303 variants that they discovered in the high quality, but not in the low quality. The low quality missed 3,343 letters. And in this particular column means we found it in only one of the 143 men. This column over here says, and this still shocks me to this day, even though they went over, on average, the sequences of 1,244 men 4 times, and they took out 143 of those men as a subset. Of those 143 men, there are some DNA variants that they missed in all of them. How do you miss it in all of them? And what's the chance that you go through a whole bunch of different men, randomly isolate their DNA? You shouldn't miss that much, but they did. But this is what the technology does. The bigger point I want to make here, though, is this tall graph. Now, there were some outliers in this particular study of 143 men, some who just, they missed a whole bunch in one man. Maybe, I think there were about, here they say that 4 outliers who had a whole bunch of missed variants. The rest of them, though, they said there was a median. You can think of that kind of like an average. It's not quite that, but on average, you could say, of these 143 men, 12 variants were missed in the low quality versus the high quality. Let me explain this again. If you compare a set of low quality, low coverage sequences to high quality, high coverage sequences, on average, in each individual man, the low coverage will miss 12 variants that are unique to that man and not found in anyone else. Why do I say that? When you are comparing fathers to sons and their Y chromosomes, you are looking for variants, mutations that are unique to the sons and not found in the father and usually not found in anyone else. My point is, we already know from the mainstream literature itself, because they experimentally tested this, that if you do low quality, low coverage, you're going to miss precisely those variants that are at the heart of the mutation rate question. This is what I was getting at. And again, if you want more of the technical details, you can look up this paper on our website. The Answers Research Journal. This particular paper published in 2019. And again, some of the research began around 2017-18. And here's the table from that paper that looks at the 4 different studies. The 2 Chinese men, common ancestor in the 1800s, that's this Xu et al. 2009. And their coverage was about 15-fold. And here's the complicated number that they reported in terms of the mutation rate. Helgeson et al. 2015 was another low coverage, only about 12-fold coverage, study of a whole bunch of Icelandic men who had pedigree, known pedigree relationships. Some might be father-son, some might be, hey, we had a common ancestor in the 1600s. Get the Y chromosome sequences, compare the Y chromosome sequences, count the number of differences, there's your mutation rate. They got a very similar number to this first one out here. These 2 studies represent high coverage, so 35-fold coverage, much higher quality. And again, based on what I just told you, we already expect them to discover more mutations between fathers and sons, because if you do low coverage, you miss DNA variants, for whatever reason, that are unique to individual men. Same thing right here. So the difference between these 2 high-quality studies is not just the fold coverage, but the Carmen et al. The primary purpose of that study was not to measure how fast or slow the Y chromosome mutates. They were looking at 323 men from around the globe and trying to understand human history. As a control to make sure their methods were working, they looked at the DNA between I think about 31 father-son pairs or brother-brother pairs. So brother-brother, they have a common father. You're looking at a known genealogical relationship. How fast or slow does the DNA mutate? And again, unsurprisingly, given what we know about what high coverage and low coverage can and can't do, things you're going to discover with high coverage that you don't find in low coverage, their mutation rate, again, if you're not familiar with scientific notation, this number is 10 times higher than these numbers. The mutation rate was detected to be 10 times faster. Again, if you haven't followed what I've said so far, I gave the background to why high quality versus low quality, high coverage versus low coverage is known to make a big difference in what you can and can't detect. And the way this experimental measurement of father-son mutation rates played out, it played out exactly in line with those expectations. Moretti et al. Was a study of 50 Danish trios, trio meaning father, mother, offspring. The goal of this paper was, in fact, explicitly to find out mutation rates from parents to offspring. It wasn't strictly focused on the Y chromosome, and I'll talk more about the other types of DNA that we're looking at in a moment, but it was a mutation rate focused paper, and I was able to extract a Y chromosome mutation rate that, again, 10-fold higher or more than these other results. My point in telling you all this is, all in the evolutionary literature, we find high mutation rates, a fast ticking of the Y chromosome clock that implies a recent origin for mankind just 4,500 years ago, and it's in line with what we know about the technology of DNA sequencing. Okay, well, these are mainstream papers. I'm just summarizing what's out there. So how did the evolutionary community react? They literally filtered out data that didn't fit. You can't make this up. Truth is stranger than fiction. I talk a little bit about this, refer to this briefly in the book Traced. Let me show you now exactly how this happened, beginning with this Carmen et al. 2015 study. Here's a supplemental material. In the main text of the paper, they make it sound like they found a mutation rate in line with evolution, something that fit their expectations. In the supplemental material is where you get the details. They said the number of FS, so that right here they define it, father, son, brother, brother differences. The number of father, son, brother, brother differences is approximately 10-fold higher than the expected of de novo mutations, so just mutations arising from fathers to sons, considering the range of published chromosome Y chromosome mutation rates. And there they cite the low quality Xu et al. Study, 2009, which was two Chinese men of a known genealogical relationship. This is based on DNA from fossils. It isn't even a father-son mutation rate. This is extrapolating. This doesn't measure the mutation rate directly either. And this is, again, not a direct measurement. It's basically from evolutionary expectations that we expected the mutation rate to be 10-fold less, and we found something much higher. This finding prompted us to explore additional filters. They said this, and you can look at the data. The explicit justification is we used, so let me just clarify something here. Again, when you're doing DNA sequencing for the Y chromosome, you do apply filters. There's 60 million letters total. We can't access 50 million of them. With current technology, we have to apply filters to only look for this particular region. But that filter is based simply on experimental, or I should say, empirical technological limitations. What they're saying here is not, hey, we had technological limitations, we had to do something else. It's, this didn't agree with evolution, and so we invented a filter to make it match. Literally, they filtered out mutations that didn't fit evolution so the numbers would make sense. This number right here is not their final reported number. Fortunately, they gave you in a supplemental table the step-by-step filtering process so you could say, okay, what is the actual number of measured mutations independent of evolutionary filters, just based on technology? That's the number. What about this over here? This story gets even wilder because there's follow-up to it since I've published the paper and the book that I'll refer to here briefly. Now, I will say in the future we'll have separate episodes dealing specifically point-by-point responses of critics to some of this science. In this little mini-series, I'm simply trying to lay out for you the history of what's happened leading up to Traced. So here's the paper that I referenced, 150 genomes, which is the 50 trios. So 50 groups of 3, which is your 150 total DNA sequences. Again, there is some aspect of the paper that does look at the mutation rate in the Y chromosome, fathers passing on erroneous copies. But the primary focus of the paper is what we're going to call autosomal DNA. Just think of this as the DNA you get from both parents. And again, from mom's side, from dad's side, in mom's egg stem cells, we live in a fallen world, there are mistakes that occur. every generation. That's what they're measuring. On the father's side, in his sperm stem cells, mistakes are occurring every generation. And they are almost exhaustive in studying this. I'm not going to walk you through these various figures. They look at single letter changes. I've basically assumed that for most of our discussion so far. That's where, in terms of the absolute number of individual variants, that's the vast majority of what we're looking at, which is why they spend so much time on it. There is a minority of differences between various people that are called indel, an acronym or an abbreviation for insertions and deletions. Sometimes when your DNA copying machinery is copying the DNA, it skips a section. It skips 5 letters. It deletes 10 letters. It adds accidentally 10 letters. These sort of short sections or chunks of DNA instead of single letters is what are the indel rates. They're looking at those. You can see here a blue line, a red line. It's already been known, and they confirm this here, that older fathers will pass on more mutations than younger fathers. Older mothers, not so much so. There's a biological reason for this, namely that ladies produce their eggs at puberty, and so cells dividing stops for them. A 40-year-old mom, biologically, is almost the same as a 20-year-old mom. Whereas for men, the sperm stem cells, sperm are produced throughout a man's lifespan. And so a 60-year-old dad, a 50-year-old dad, biologically looks much older than a 20-year-old dad because his cells have divided much more. There's been many more opportunities for mutations, and you can empirically measure this. Okay, why am I telling you all this? Because I want to summarize for you what this paper did and did not do, and the silence of this paper is what's telling. So again, they looked at single letter mutations, they looked at chunks, which we call indels. For the DNA we get from both parents, fairly exhaustive there. Exhaustive for single letter mutations. For chunk or indel mutations, they looked at the Y chromosome mutation rate. For indels, and not a word about the single letter changes. Why would they admit that? That's the focus of the whole paper, is mutation rates. In one of the last figures of the paper, they did publish a family tree based on the single letters of the men. They applied a very conservative filter, meaning of the 10 million letters, there's about 9 million, this is already again in the literature, based on the limits of technology that you can especially access in an unambiguous way. They give that detail. They also gave a scale bar down here for how long the branches are, how many mutations each branch length represents. I found, because I knew there were 17 father-son pairs based on what they said, in this tree, again, there's 50 dads plus there's some of the sons, and not all the offspring are sons. So 50 plus something. I found the closest pairs on this tree, the 17 closest pairs, treated those as the father-son pairs, used this scale bar to extract the number of differences between fathers and sons. And that's how I derived the mutation rate from the raw data. Wouldn't provide it. Now, what's happened since then, since the paper, since the book came out? A critic, an evolutionary critic, emailed the authors of the paper. The authors said, he emailed them basically saying, as far as we can tell, because this guy Herman Mays wouldn't actually publish the full correspondence. He's hiding something too. He publishes just select elements from his correspondence with the authors of that Danish study. And here's his quote from the email response. They said the error rate is 1 in 1,000. In other words, whenever you're doing DNA sequencing, for whatever reason, there's errors that occur. There's still some limits to technology, which you could mistakenly interpret as biological mutations. Instead of it's just a fluke of technology. So they said, well, no, see, what's really going on here is he's just detected flukes. Now, elsewhere, Herman Mays quoted from them, and they did indeed confirm that I did find the 17 father-son pairs. They just said, no, sorry, those differences he's talking about are not real mutations. Those are just limits of the technology. Do you think they published the data to justify that conclusion, which is the normal way you adjudicate scientific debates? They did not. So the first time when they published their paper, they could have published the raw data. They said nothing, did not publish the raw data. A little bit of it slipped through this tree. Then they're made aware of it. Hey, the creationists are using your data to justify their conclusions. Oh, they're wrong because we say so. And it's not just because we say so. Again, this is their second chance to publish the raw data, and they won't. So why not? They say, well, he can't be right because if you look elsewhere in the literature, we don't see any evidence of a fast mutation rate. And what's one of the studies that he cites, these authors cite? Carmen et al. where the authors literally filtered out data that doesn't fit evolution. Some of these other studies are forms of circular reasoning. He cites the Shu et al. 2009 of low quality. I'm thinking to myself, how can these people who are publishing mutation rate studies and talk about the Y chromosome not even be aware of the details of the literature in their own field? The data that they did publish, from which you could extract the raw information, is in line with what we know about mutation rates. Again, in this case, they're just omitting the data entirely. What I've just showed you about the conclusions fits what's known in the literature about the limits of technology. I have a feeling they didn't publish the data the first time or the second time and simply said, trust us, it's wrong, because the rate is too high. We already have an example of this. Now, let me highlight something here. One of the common criticisms of creation scientists, that's factually an error, is that creationists don't publish in the peer-reviewed literature. We do. That paper from 2019 is in the peer-reviewed literature. We have people with terminal degrees who criticize the paper and try to find flaws. What the evolutionists will typically say then as a follow-up is, well, you didn't have evolutionists peer review your paper. True, because many of them don't want to. You can see a debate I did with Herman Mays, the same guy who was emailing these authors, where I asked him basically to, in public, review my book, Replacing Darwin. And anyway, I can point you to that video later, or you can look up on our website. And the write-up I had about it, you watch for yourself. He basically refused to engage the arguments. So even when we try to ask them explicitly for review, that doesn't happen. But I want to say something else here. If the standard of peer review is having your ideological opponents review it, who's reviewing the evolutionary literature? Do the evolutionists ask creation scientists to review the literature? And in light of what we just observed, going back to that Carmen et al. Paper from 2015, where they explicitly say, because of evolution, we're filtering out data, isn't it high time that creation scientists review the literature? Given what happened with this Danish paper, where they're not talking about and not giving the raw data, except in this type of form where you can still extract from it the results, isn't it high time creation scientists review the evolutionary literature? So I'm happy to engage the debate over peer review and such. In a sense, that's kind of what I'm doing here and what I did in my paper, say this is what they've published and here's what they're saying and here's the patterns they've already established, and the conclusion that's rational to draw from all this is that the clock ticks fast. Here's really the bottom line here. If you say, okay, the clock is fast, so how many mutations should occur at this fast rate, which, just to translate those scientific notation numbers to something more practical, the bottom line from this table, let me just go back to it before I go to this graph right here. The rate of 3 times 10 to the negative 7th mutations per base pair per generation, all that technical terminology means, on average, in that section of 10 million letters, about 3 mistakes happen every generation. 3 mistakes. Well, if you do that for hundreds of thousands of years, which is what the evolutionists say, anatomically modern humans have been around for that long, you get a lot of mutations, way more than what we actually observe. These bars represent the statistical range here. Whereas if you take that fast mutation rate you applied over 4,500 years, you capture almost all of what we see. You don't capture this right here. What is this referring to? It's these launches in the tree right here. So it's an error. No, or I should say, no one's actually measured the mutation rate among men in these branches. And one of the predictions that I've put in print, because science is about making testable predictions, is that once someone actually measures the mutation rate in some of these long branches, the label is just haplogroup, especially in haplogroup A00, some of the very longest branches. This tree doesn't even have the very longest of the long branches. It'll have a mutation rate that's even faster than 3 mutations per generation. My point is, the evolutionary literature has measured father-son mutation rates. Some have been of low quality, some have been of high quality. We already know from the evolutionary literature itself, low quality sequences will miss variants that are unique to individuals. Unique to individuals, and that's the definition of looking for mutation rates between fathers and sons. Are there any DNA sequences, any variants that are unique to the son? And when we look at what the evolutionists have published, the low quality coverage misses a lot of mutation rates, misses a lot of variants compared to the high coverage, high quality. And when you look at the high quality ones and the implied fast mutation rate, you get a conclusion of humanity originating just a few thousand years ago. And this further makes additional testable predictions. And again, I say it's a prediction. It's not an argument against it because no one's actually measured it. And my challenge to my evolutionary colleagues is, if you want your views to be considered scientific, predict for me the rate at which these long branch individuals are going to mutate their DNA, put something in print, and then let's go into the lab together and measure it. That's the way science is done. That's just step one in this historical narrative that I want to walk you through to answer the larger question, how do we know that the conclusions in TRACED are true? And the point that I'm going to come back to again and again is it's true because it's part of a historical progression of discoveries in which successive testable young Earth creation predictions keep working. This isn't the end of the story. The critics have a lot to say about, well, you can't do that, you can't do this, and here's why it's wrong. Well, the way you evaluate that is by doing experiments, making predictions, and evaluating them in the future. In other words, this is just step one of a larger narrative, a longer historical narrative, in which we kept testing the predictions that flow from this. The faster mutation rate in some of these long branches isn't the only prediction that flows from this model. So I hope you'll tune in next time where we talk about step two in this process, the longer narrative in which we have predictions, fulfillments, more predictions, fulfillments, meeting this gold standard of science that evolutionists have laid down for decades for creation science. I would argue that creation scientists are meeting and exceeding the standard that evolutionists are not. And that's what adds to the validity of the conclusions in this book. I referenced this earlier book as well, Replacing Darwin, The New Origin of Species, that talks about the wider creation evolution question. I wrote this really for a skeptical audience, someone who doesn't agree with me. 10 chapters of science, ends with the gospel. So if you're a Christian watching and you say, well, can I give this to, what if I'm interested in evangelism? That's part of what I had in mind. In addition to the scientific goals, this book, Replacing Darwin Made Simple, is sort of the Cliff Notes version of that, thinking explicitly of a church audience. Again, if you're watching this, you've got questions, there's ways to connect with me on social media, and happy to correspond that way. Stay tuned for more to come. This is just the first step in looking at the science behind traced human DNA's big surprise. There's more to the gold standard that I want to show you, how creation scientists are meeting and exceeding that. We'll have more to come, so I hope you'll stay tuned. And I'll turn it back over to Brian.
Oh, that was absolutely incredible. I love seeing how real science confirms the Bible again and again, and how you're making testable predictions and those are being fulfilled. We look forward to the coming predictions and their fulfillment as well, Lord willing, as you do all this science. And it's interesting to watch as you are kind of laying out what's been going on behind the scenes, how so many people who hold to the evolutionary worldview, they hold to it with religious fervor. It must be true. Nothing else can be true. It is their ideology. They are clinging to with everything they've got, and they don't want to let it go. And that shows in what they're doing and what they're not doing in the realm of science. And really, what we're seeing here is that real science, done by you and others, rooted in a biblical worldview, exceeds that gold standard of science. And in many cases, evolution cannot meet that bar because of just the basic philosophy behind it and the ideology behind it. And so wonderful to see that. We are so excited about the coming research and what that's going to look like. Guys, again, you've seen it a couple times, but you'll want to check out this book for more details on this. We're just scratching the surface on the book Traced, seeing how real science confirms the Bible. And I cannot wait till next time. We'll see you then. Take care.